All right, so we're on our last section, 3A.8, part A, tangent function vocabulary is where we're going to start. We really haven't talked about the tangent function yet, have we? Oh, no, we have not. Well, the time has come for us to discuss the tangent function. So here we go. All right, so when we are talking about the tangent function, remember we kind of talked about it's that relationship between your sine and cosine, right? Using the quotient rule. And so just when we're describing it, we have to keep in mind that at some point, a zero can be in the denominator, right? And when a zero is in the denominator of a rational function, what does that produce? Undefined. And graphically, what would you see? Nothing. What is that nothing called? What is that invisible space called? It's an asymptote. It creates an asymptote at that undefined point. So tangent functions have asymptotes because of that. Okay, because cosine cannot equal 0. Try that again. Okay, we have asymptotes. Okay, the tangent curve is what the graph is called. And again, it's the ratio of change from your y values to your x values between 2 points. Okay, so we're going to look at the tangent function and we're going to make some key points. So the tangent graph will complete one full cycle in the interval of 0 to pi, okay? Meaning that the period is pi. So instead of like cosine and sine that have a period of 2 pi, tangent only has a period of 1 pi. So the period is going to be 1 pi. So our period equals 1 pi. So when we're looking at determining what is the tangent of each point, if you have your unit circle out, essentially what we're doing is we're going around and doing y divided by x at our key points. Does that make sense? So from 0 to pi, we're doing y divided by x to determine what is our tangent value. Okay, so you pull out your unit circle. Here we go. Okay. All right, so we're at the tangent of 0. So tangent of 0 is going to give us what over what? 0 over 1, which makes what? 0. So the tangent of 0 is 0. Now we're at the tangent of pi over 6. At pi over 6, what do we have in the numerator? 1 over 2. And in the denominator, we have square root of 3 over 2. After we keep, change, flip, what are we left with? Square root of 3 over 3. Okay, moving on to the tangent of pi over 4. What is our numerator value? Square root of 2 over 2 divided by square root of 2 over 2. So what does that make the tangent? 1. Okay, now we're at pi over 3. Our numerator is now square root of 3 over 2. Our denominator is now 1/2. So keep, change, flipped, and we're left with square root of 3. Do we all understand where these numbers are coming from? Okay, now we're at pi over 2. At pi over 2, what's my numerator? What's my denominator? Oh no! So that makes it what? Undefined. Okay, now 2 pi square root of 3. So the tangent of 2 pi square root of 3, what do we know tangent has to be in quadrant number 2? Negative. So in quadrant number 2, we know that all these tangent values are negative. Okay? Okay, so 2 pi over 3 is going to be negative square root of 3. 3 pi over 4 is going to be negative 1. 5 pi over 6 is going to be negative square root of 3 over 3, using their reference angles in quadrant number 1. Does that make sense? And then last but not least, what is pi? 0. So it says determine where we are increasing.
0 to pi over 3.
So we're increasing from 0 to, it's technically pi over 2, just not equal there, right? So we're increasing from 0 to pi over 2, but it's not a bracket, it's a parenthesis. Does that make sense? Because we're not included. And where else?
Let's see. Oh, wait,
Mhm.
5 pi over 6 to 0. Oh, pi over 2 to
Pi.
y.
These values are increasing
Oh, because they're negative.
because they're negatives. So it's the opposite of what you think.
Oh, so they're getting closer to 1.
They're getting closer to 0. Yes.
Well, done.
Okay. Is there any interval where I'm decreasing? No. Because we've used all of them. So no intervals of decrease. I already spelled decrease. I'm going to get there. Okay. When there's no intervals of decrease or it's just one motion taking place, this is called a, just for fun, monotonic.
Just for fun, right?
Just for fun. Okay. It's only increasing on its domain. Monotonic. Mono meaning one, you know? Okay. One. Really? Okay. All right. So now let's create our graph to see what this looks like. So again, when we are graphing this, it is usually shown from negative pi over 2 to pi over 2. You actually do not start at the origin or start at your y-axis like you do with sine and cosine. You typically start from negative pi over 2 to 2. That's just so that you can see your full asymptotes, okay? So when we graph our tangent graph, we are going to have asymptotes at pi over 2. Why do I have an asymptote at pi over 2? It's undefined, right? So at pi over 2, it's going to be undefined. And that means also every other 180 degrees, it's going to be undefined. So I'm undefined at pi over 2. I'm undefined at 3 pi over 2 and negative pi over 2 and negative 3 pi over 2. So at all of our odd half values. Does that make sense? So if we're looking at it, we're looking at our odd half values. Okay, we're going to graph our continuous function from negative pi over 2 to positive pi over 2. What makes it continuous is that there's not an asymptote splitting it as if it was if I started from 0 and worked my way to pi. Does that make sense? If I went from 0 to pi, there would be a discontinuity in the middle of my graph. So that's why it's from here to here, yes. But usually for the parent function, we're focused at negative pi over 2 and pi over 2. Okay. All right. We're going to graph what we do know. What was the tangent of 0? 0. What was the tangent at pi over 4? What was the tangent at negative pi? Well, which would be, there we go. So now when I draw it, you said square root of 3 and I ignored you.
Wait, so you can't draw anything in the little holes?
And the
little gaps?
they're asymptote. Okay. So here, and then it's going to continue. So you're halfway. Negative 1, 1, and then it's a curve. It's our extra sassy graph. what I call tangent, the sassy graph. She got a little curvaceous walk to her. It's just extra.
Or some scoliosis.
Or bad scoliosis, you're right. The function with scoliosis. Cool. All right, so our point of inflection is where our rate of change occurs. And so in this case, it changes at our 0, right? So where it's changing from being concave down to becoming concave up. That is our point of inflection. So our point of inflection is x equals 0, but because it happens every other pi or every other 180 degrees, it is a continued function. So we write it as 0 plus pi times a k value.
What is our p value?
I'm about to tell you. K is any integer. Does anyone remember the symbol for integer from Algebra 1?
It's that little 3. Integer, is it the cursive I or no? I didn't know there was a symbol for it.
What did y'all learn in Algebra 1?
Oh,
I keep forgetting. I'm sorry. It's a Z. It's the Z.
Oh, wait, yeah.
The integer symbol is Z.
Wait, see, that was what's the thing in between? Yeah, that means.
This means exist. And instead of writing the word exist, we're lazy. So this means, what is K? K is any integer. That's what this is meaning. K can be any integer. Remember what integers are. Our whole numbers and their opposites. Y'all remember that? Your integers are your whole numbers and their opposites. Okay? So it could be, well, when it's 0, it's at 0. But it could be 1, -1, 2, -2, 3, -3. Okay, it cannot be a fraction because it's a integer. Exactly. No, fractions are our friends. Y'all sound like haters, but fractions are your friends. Okay? All right, now the domain here is very unique. The domain is unique because unlike sine and cosine, it is not continuously on the going from negative infinity to positive infinity, is it? No, it has little stopping points. There's discontinuity in my graph. There's an asymptote in my graph. Actually, there's multiple asymptotes. Okay, so just how we wrote our point of inflection, we're gonna have to write our domain showing that there is multiples of it taking place. Okay, does that make sense? This means exist. It's part of. It exists. I didn't like writing the word. K exists is an integer. Yep. It's like if C and E had a baby, this is what it would make. Like if C and the letter E made a baby, that's what that symbol makes.
Oh, I thought you meant like C, like A, like on our.
It's a C with a. Oh no. It's like a little extra. All right. So how do we write this? Well, the first thing we have to state is that our B times our X cannot equal pi over 2 or plus any of its multiples. Okay, so B times X cannot equal pi over 2 plus any of its multiples that take place. Yes. So what that means is that our multiples are where our asymptotes take place. So if I let K equal 3, that means that pi over 2 plus 3 pi is a asymptote. It cannot exist there. It exists everywhere else except at these asymptotes.
Oh, pi over 2 plus pi, that's a fraction?
Yes.
Okay.
And again, K is only an integer, because it can be the whole or the opposite. This means that your point of inflection, where your concavity is changing, right, takes place at first at 0, and then it takes place again every 180 degrees. So every pi that takes place. So this is 1 pi. If I keep going, it's going to happen again at 2 pi. If I keep going, it's going to happen again at 3 pi. If I keep going, because there's infinite of them, all we can do is write it as a equation versus stating exactly where the point of inflection is. So I'm thinking that if they ask you for the domain, it'll be a multiple choice in my brain, and you would have to be able to select the one that represents it. I don't think they're going to have you just write the domain. No, tangent's its own beast. This is just one cycle. This is a continuous cycle. That's all this is. This is one cycle of tangent, but that pattern goes on forever, over and over and over. Asymptote, sexy curve, asymptote, asymptote, sexy curve, asymptote. Okay, it keeps going. Yeah. My bad. My bad. But your range is obvious. What is your range? All real numbers. It goes from negative infinity to positive infinity. Okay. Your x-intercepts. What's happening with them? They're every pi. Because they're every pi, we're going to write it as pi times k. And again, k represents what? Integers. Every integer. So my intercepts are at 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Okay. These are, if you think about it, do y'all remember when we talked about arithmetic sequences? These are sequences, right? That's what these are. Yes? Huh? Yes, because you have to define what k is. K is an integer. You can write it in words if it makes you feel better.
Oh, we could just write K is always an integer.
K is an integer. If you don't want to use exist or the Z for integer, you can write K as a integer. I don't know. Easy one. Where's our y-intercept? Okay. What type of symmetry would you say this function has? Odd or even? It's odd. I wrote it there for you. I meant to just write symmetry. And I'm glad you see that. The answer is there for you. It is odd symmetry, which means that it goes through the origin and it has rotational symmetry. Meaning, if I was to rotate my graph 180 degrees, the image is still the same. If you don't believe me, turn your paper upside down. The image isn't the same. Well, those are your drawing. Yeah, because parabolas are even functions with y-axis symmetry. All right, now our asymptotes. Where are our asymptotes happening at? And that pattern continues on and on, right?
Yeah.
So when we write it, our vertical asymptotes are at x equal pi over 2, but also its multiples every k. Does that make sense? Because it happens at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. I call them my odd halves. I don't know if that helps y'all.
Your what?
The odd halves. I call them the odd halves because that's when the odd numbers are in the numerator. It's going to simplify, and that's where our POI is. The odd halves is helping. You can admit it. Thinking about it as odd halves. All right, now we're going to think about what is the pattern that's taking place to help us remember our graph. So remember with sine we have intercept, max, intercept, min, intercept, right? Yeah. With cosine, we have max, intercept, min, intercept, max, correct? Now, looking at tangent, we're going to have asymptote, followed by a low point, asymptote, followed by a low point, followed by an intercept, followed by my high point, followed by an asymptote. That's going to be our pattern here. Asymptote, low, intercept, high, asymptote. Do we see it? You know? I was like, Miss Low, who's that? Who?
I was thinking about the Trullo, my assignment experience, and then I was thinking about you.
We don't put those together. We don't put those together. All right, so starting off when we have it normally, what values are we at for our asymptote? So our asymptote is at, first one is at negative pi over 2. So we're at negative pi over 2. Our low, huh? Yes, I'm writing it out.
Wait, why would the low be pi?
Negative pi over 4 is our low point. Negative pi.
Oh, on the, okay, I see.
Our intercept is at the origin, 0, 0. Guys, our high point is at positive pi over 4 and 1. And our asymptote is back at positive pi over 2. So these are the points that will be shifting or transforming when we get to transformations. This is our parent function for tangent. Sorry. All right, let's start with a easy shift. So we're going to start off with just a negative tan x, okay? So negative tangent. And what happens with negative tangent? Our highs and our lows are switching. Anything else is going to change? No, because it's 0, right? And 0 times anything is still going to be 0. So because of the negative tangent, because, guys, I can stop teaching. You can teach yourself. It's totally fine with me. Let me know. Okay. Your A is less than 0, which means that your A is negative. So when we're talking about it, we're going to be an asymptote. But now instead of being a low, we're going to be a high, then intercept, then low, then our asymptote. Yes. Okay. So we're still at negative pi over 2. We're still at pi over 2. Our intercept is still in the center. But now, instead of being a low, we are a high. Instead of being a high, we are now a low. So our curve is now decreasing. And then I would repeat. I don't know how many. It just says 1 period, right? But I can repeat it again. I wanted to just fill in the whole graph because it's really not that hard of a graph to draw. Okay, pretend that those are all symmetrical curves. We got good imaginations. All right, your period is still equal, your period now is equal to pi divided by b. It's not 2 pi, it is pi. Because our whole period of our parent function is 1 pi. So in this case, it's just going to equal pi because our b is what? Our b equals 1. Okay, your a equals -1, which is what caused the function to reflect. There we go. It's not amplitude. It's the absolute value of A is your amplitude. We're not talking about amplitude. It's not amplitude. It's just saying, what does your A do? Cause the function to reflect across the x-axis.
Wait, would it not be the?
Nope, we reflected across the x-axis. Pew, 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 right? Okay, so now our function is doing what? Instead of increasing, we're doing what on the domain? Decreasing. So y is decreasing on the domain. Okay, how do we feel about a negative tangent function? Okay, now we're going to go to when A is not 1 and B is not 1. Okay, so what are you doing? First, you got to find your 5 key points. So the first thing you're going to do is find 2 consecutive asymptotes by setting their argument equal to the parent asymptote. So basically, we take whatever the argument, which is your insight, that bx minus c, and we're going to set it equal to our negative pi over 2 and our pi over 2, because that's telling us how is this shifting, okay? This needs to have parentheses around it. And then from there, we're going to identify our x-intercepts, which is the midway between the consecutive asymptotes. And then we're going to find the points on the graph that are 1/4 and 3/4, so our halfway of our halves. And then we just add our additional cycles to the left or to the right as needed. So our domain here, our domain is basically saying that b times x minus c cannot equal 0. That's the general domain when you have a and b. Okay, your range is going to always be from negative infinity to positive infinity.
It will always be like this.
Mm-hmm. Your A value is your vertical stretch factor or dilation, however you want to say it. So we stretch by a factor, we're dilated by a factor, blah, blah, blah. Remember your key point pattern? So for this, our key points are asymptote, low, intercept, high, asymptote. And your period is P equals pi divided by B. Okay. And then we apply just like we did with sine and cosine. All right. So keeping these things in mind, again, we are thinking about it in 4 partitions. So you have 1, 2, 3, 4. So your beginning, your ending. We're going to find our halfway, our quarter, our 3/4 of the waypoint, and go from there. Okay, so we're going to now go and try and apply all of this and see what happens. So first, it says to graph y equals negative tan x divided by 2. Don't know where my graphs went. I did have graphs on here, but my graphs have disappeared. So we're going to first determine our A and our B. So we know that A equals negative 1, and we know that B equals 1/2. Okay. So from determining that B equals 1/2, we'll be able to determine our period and find our asymptotes. All right. So our period equals pi divided by 1/2, which equals 2 pi. So now we're expanding over 2 pi of time. So that means that our asymptote is going to have to go from negative pi to positive pi. Okay. Another way of looking at that is just how to determine exactly where your asymptotes are. So to find our asymptotes, to find our left side asymptote, we're going to take our inside, our argument here, x over 2. And we're going to take x over 2 and set it equal to negative x over 2, negative pi over 2. To find our right-hand argument, right-hand asymptote, we're going to take x over 2 and set equal to positive pi over 2. Okay, quickest way of doing this is through cross multiply and divide. So when we cross multiply, we get 2x equals negative 2 pi. So therefore, x equals negative pi. That's going to be our first asymptote, our left-hand asymptote. Cross multiply and divide here, and we get 2x equals 2 pi. So therefore, x equals positive pi. And that's going to be our right-hand asymptote. So when we're talking about our graphs, we know that I don't know, I really would like my graph here, but I don't have it. So we're just going to kind of do it as a quick little sketch here. Grab another color. We now know that we have an asymptote at negative pi. We have an asymptote at positive pi. We still have our halfway point. Okay. And now we still have our max and our min because there is no vertical stretch. So our max is now, and our high point, I'm sorry, our high point is now here because our A is negative. And our low point is now here at our halfway. So we're at negative pi over 2. And we're at positive pi over 2. So now we have our tangent function after our transformation. All right, we're going to repeat the same thing here. We're going to identify A, B in our period. So A equals positive 1, B equals 1, 4, because it's pi over 4. So therefore, our period equals pi divided by pi over 4, which equals 4 pi. Well, not 4 pi, equals 4. I can do math because your pi's are going to cancel out. So you get 4. Our B is pi over 4. Read it right, 4, 1, 4. Okay, so now we have 4. So you know that we're expanding from negative 4 to positive 4. To double check that, you're going to identify your asymptotes. To find your asymptotes, to find your left-hand asymptote, you're taking your argument, which is pi over 4x, and we're going to write it as, so it's negative pi over 2 equal pi x over 4. And then your right-hand asymptote is going to be positive pi over 2 equals pi x over 4. Now we cross multiply and divide. So we get negative 4 pi equals 2 pi x. After we cross multiply and divide, our pi's are going to cancel out. And we get x equals negative 2. X equals negative 2 is our left side asymptote. Again, cross multiply and divide. We get 4 pi equals 2 pi x. So x has to equal positive 2. So we're going to draw a little sketchy sketch of our graph. Okay. Freehand sketches are not always the most beautiful, but we know that we start at negative 2 as an asymptote. So we have negative 2 as an asymptote, and we have positive 2 as an asymptote. And we have positive 2 as an asymptote. Our halfway point is at 0. Our A is positive, so that means we're going to still start off as a low and then a high. Halfway between negative 2 and 0 is going to put us at negative 1, and negative 1 is going to be down here at negative 1. Halfway between 0 and 2 is positive 1, because our A is 1, is going to be our high point. So our graph looks like, I'm pretty sure yours is going to look way better than my curve, but there's our curve. And then it will repeat the pattern left to right. I can't even accept that as a curve, y'all. I thought I was okay with it, but it's not. It's not okay. It's terrible work. Let's try that again. That one didn't even go through all the points. Okay, I don't know why I'm struggling with drawing this, but it's just sad and tragic. I don't need the extra commentary during my review. Okay, guys, I'm gonna give up on drawing this. Just gonna let tangent. This is not gonna be one of our sexy tangents, but you get the gist. Okay, so hopefully it's not too terrible finding your asymptotes, halfway points, and you got this.